Bangladesh, hemmed in by India and the Bay of Bengal, is one of the most populous countries in the world. More than 122 million people live in an area only 4 times as large as that of the Netherlands. The huge rural population plants rice and jute and supports itself by fishing. The great floods of 1987 and 1988 and a cyclone in 1991 were very damaging to the country. The Brahmaputra, Ganges and Meghna rivers meet in Bangladesh, causing much of the flooding. The Jamuna River forms the lower reaches of the Brahmaputra, cutting Bangladesh in half. The Bangladeshi use ferries to transport goods and people across the river from east to west and vice versa. Ferries are the only means of transport for crossing the river. The waiting times are often very long and sometimes mount up to days. The government has therefore decided to build a bridge across the Jamuna River with the help of international donor agencies. The bridge will make it easier to reach the western part of Bangladesh and the hinterland of India. The Jamuna Bridge will be a multi-purpose bridge. It will be used to transport goods and people both by road and by rail, and it will also transport energy by means of a transmission line and a gas pipeline. In terms of water discharge capacity, the Brahmaputra is the 4th largest in the world. For sediment transport, it is the 2nd largest. Depending on the season, its width varies from 5 to 15 kilometers, with a depth ranging from less than 2 to more than 20 meters. To build a bridge across this untamed braided river is a major challenge, as its channels and bank lines are constantly changing. In an early stage of the studies, it was decided to locate the bridge some 8 kilometers south of Sirajganj. Here, the river in the dry season is relatively narrow, 4 to 8 kilometers, and a 5-kilometer bridge would be long enough to allow for the passage of a large flood. Deeply founded 3 kilometers long guide buns were introduced at both sides of the river. They protect the bridge abutments and the road and rail approaches in the floodplains behind it. Some 7 kilometers north of the bridge, the town protection works of Sirajganj and the shore protection works at Burapur at the other side of the river form so-called hard points. The hard points, together with the guide buns, form a system of river training works which forces the river to continue flowing under the bridge in years to come, and to stop locally its channels from shifting in eastern and western directions. A consortium of 3 consulting engineering firms, Rendell, Palmer and Tretton of the United Kingdom, Netherlands engineering consultants Nedeco of the Netherlands, and Bangladesh Consultants Limited made the studies and designs for the $1 billion project and is now supervising its construction. Design and construction of the bridge is done by the Korean firm Hyundai, while the river training works are constructed by Ham von Ord ACZ, a Dutch consortium of dredging and marine contractors. For Nedeco, the Dutch firm of consulting engineers, HASKONG takes the lead. HASKONG is specially concerned with the design of the river training works and was assisted in the early stages of the project for this purpose by Delft Hydraulics and Rijkswaterstaat. In 1994, at the end of the flood season, and 7 months after award of the construction contracts and start of mobilization, the project was inaugurated by the then Honorable Minister of Communications of Bangladesh, Oli Ahmed, and construction started immediately afterwards. During the first construction season, a work harbour is dredged, working areas are reclaimed and offices and homes built. There are a total of 63 houses, 60 studios and 2 buildings with dormitories. There will also be a clinic, sick bay, a restaurant, bars, squash and tennis courts, a library, a basketball court and a swimming pool. This residential area will be handed over to the Jamuna Multipurpose Bridge Authority by the end of the project. Apart from these activities, the river training contractor focuses on 2 tasks during this first season: the supply of rock and boulders for the project and the construction of Brahmaputra hard point. The boulders come from the riverbeds in the northeast of Bangladesh. A total of 770,000 tons will be needed for the entire project. However, only these boulders come from Bangladesh. The rest of the rock has to come from quarries in India, Bhutan and Indonesia. A total of 1.5 million tons of rock will be used. Most of it will be used in the large guide buns built on both sides of the river. Getting those 1.5 million tons of rock in the heartland of Bangladesh is a major logistical problem. More than 800,000 tons of rock come from various quarries in India. Unlike most countries, stone cutting is still done by hand in northern India. The river training contractor employs Asian supervisors who monitor quality and production planning on the spot. In addition, there are regular visits to the quarries by the consultant's supervisory staff and by the contractor's staff to make sure that the delivery targets are met. The transport of rock to Bangladesh is extremely complex. Part of the rock goes by rail. Each train carries around 1,600 tons of stone. However, India's railways do not have enough trains. There are only 4 to 10 available per month. The trains go to the Bangladesh border. There the rock is transferred to Bangladesh trains, which then transport the rock to the west bank of the Jamuna near Siranjganj. The rest of the rock from the northern India quarries comes by truck. Not without problems, since the border crossing with Bangladesh entails long delays. These countries have a different way of doing things. Waiting times of several days are not unusual here. At this time, the border is closed for a religious festival. When the trucks finally pass the border, they will have to be unloaded several kilometers down the road. The Indian trucks have not received permission to travel inland. The Bangladeshi want to handle the transport themselves so that they can earn their share. The Bangladesh trucks transport the rock to the West Bank, where they are loaded on local country boats and finally reach the destination on the other side at the work harbour. Rock weighing some 60 kilos again go from hand to head. The largest quarry in Asia is the Karimun quarry in Indonesia. Here, some 250,000 tons of rock are produced for the Jamuna project. Fragmentation takes place in this quarry using drilling equipment and dynamite. To transport the stones through the Bay of Bengal to Bangladesh, special barges were built by the contractor in Singapore. Between 5,000 and 6,000 tons of rock are shipped per trip. In Bangladesh, the barges are towed up the river to Shantpur. In the middle of the river, there is a transfer pontoon. Here the rock is transferred to smaller river barges, specially built by the contractor for this project. The river training contractor also acquired push boats to bring the river barges in pairs to the project site. Cumbersome but necessary, as the large barges from Indonesia and Visakhapatnam, India, have too much draft for the Jamuna River. Depending on the river's water level, the smaller barges each carry between 1,600 and 2,400 tons of rock. The push boats cover the final 200 kilometers in 2 days. When the push boats arrive at the work harbour, the loaders and dump trucks are ready to bring the rock to the depot. Once the barges have been unloaded and the push boats have taken on provisions, they return to get another load. The transport will take more than 18 months. The stock of rock must be constantly replenished so that work can continue. Before the rock reaches its final position, it would have been handled 8 to 10 times. At Buapur, a local clay bank has always prevented the river channels from shifting eastward. This erosion-resistant clay bank is now strengthened as part of the river training works and will form a hard point. The shore protection, which will be installed, will force the river discharge to flow in the direction of the future bridge between the guide bunds. First, large quantities of soil have to be excavated. Here too, the local population is hired to do part of the work. The Bangladeshi do all the work by hand. No one disturbs the small piles of sand. It is a method of measuring how much sand has been removed per team. On projects in Bangladesh, people are paid according to the amount of sand they remove. The available time is limited, and therefore also modern equipment is used in the excavation process to meet the planning. The shore protection here is constructed with mattresses, composed of 2 kinds of polypropylene geofabric. The cells result from the way in which the layers are stitched together. The cells are then filled with sand asphalt. This is produced by the asphalt plant, which meanwhile has been erected at the work harbour. The top layers of the mattresses are green. They protect the fabric against UV light. The mattresses will soon have to prevent erosion caused by currents along the shoreline. During the monsoon season, the water rises to 14 meters above PWD, the local reference level. The mattresses are laid along a length of around 1.5 kilometers. This shore protection covers a total area of about 300,000 square meters. Soon, the mattresses will be covered with sand. A black polypropylene fabric will go on the slope. Then the stones will be placed. Afterwards, the open stone asphalt provides the finishing touch on the higher areas. The shore protection had to be ready within 3 months, as in May the monsoon season will start and the water will rise. The mattresses will bend under the presence of erosion, providing a defense against the current at greater depths. In the dry season of 1995 and 1996, the West Guide Bund will be constructed. During the past 10 years of study, design and tender procedures, the river channels have continuously shifted, and this makes the final position of this guide bund uncertain. Now at last, the location of the guide bund can be fixed. It will be built on a sandbank in the middle of the river. The position of the East Guide Bund, which will be built during the next dry season, was already fixed in October 1994, together with that of work harbour and reclamation areas. As the position of both guide bunds is now known, also the length and alignment of the bridge is known. The bridge will have a length of 4.8 kilometres. Before, only an approximate length could be given, but it was assumed that bridge length would be somewhere between 4.4 and 5.2 kilometres. Pile driving for the 4.8 kilometres long bridge starts in October 1995. The 121 steel cylindrical piles are driven according to schedule in a period of 9 months. They have a length of approximately 80 metres and are either driven in clusters of 3 2.5 metre diameter piles or in pairs of 2 piles having a diameter of 3.15 metres. The exceptional length of the piles is necessary because of the 35 to 50 metres deep scour holes which can form around these piles and the deep foundation level. All piles are driven to a gradient of 6 to 1 and arrive at the construction site in sections of 20 to 49 metres long. Each time a section has been driven using one of the largest pile driving hammers in the world, the next section is welded onto the section already driven. After a pile cluster has been completed, the soil inside the piles is removed by using airlifting, and the hollow piles are then completely filled in with concrete. The pile caps are prefabricated in the bridge construction yard. The cap is then placed on a pontoon and towed to its destination. A special floating crane lifts the cap and places it over the pile cluster. Piles and caps are then made into one unit to function as a yoke by placing reinforcement and concreting the interior of the pile cap. Finally, the pier stems of varying length are constructed on top of the pile caps, and the pier is then ready to support the bridge superstructure. Altogether, 50 piers are constructed to carry 49 bridge spans. While the bridge contractor proceeds with pile driving across the river training contractor is constructing the west guide bund. Because this guide bund will be built on a sand bank in the middle of the river, the western river channel between guide bund and west bank has to be closed, as well as some secondary channels. The closure of such channels in an alluvial environment in a flowing river requires a special technique and has to be done with great care to avoid mishaps causing program delays and high additional cost. First, the bed of the channel is protected against erosion by placing fascine mattresses ballasted with boulders. Then, a rock bund is built across the channel on the foundation of bed protection mattresses. Finally, the permeable rock bund is sealed by pumping sand in huge quantities in the still flowing water. To construct the underwater slope protection of the west guide bund, a huge trench going down 25 to 30 meters below ground level is dredged. The 17 million cubic meters of dredged soil is used to reclaim areas behind the guide bund and for the causeway to the west bank. Initially, 3 and later even 4 cutter dredgers were employed by the river training contractor to dredge the trench and form the underwater slope for the slope protection. In the final design, the underwater slope has a gentle gradient of 1 in 5 and more deeper of 1 in 6. The slope protection consists of a composite geotextile on which a 50 centimetre thick layer of rock is placed. At the toe of the slope, which, depending on the location, is at a level of 15 or 18 metre below the local reference level, PWD, a falling apron is placed. This will enable the guide bund to cope with scour holes in the Jamuna River going as deep as 43 to 46 metres below the level of the reclamation areas. The geotextile mats to be placed are so-called fascine mattresses. In the past, these fascine mattresses consisted of brushwood and reed, while in Bangladesh in the 70s, bamboo, reed and palm leaves were introduced for this purpose. Nowadays, the fascine mattress is made of a composite geotextile fixed on the fabrication yard to a bamboo frame. To obtain flexibility, the bamboo stalks placed lengthwise in the mattress are first split, and then again the strips are bundled together like the original fascines. The framework of bamboos fastened to the geotextile enables the mattress to float and to be towed to its destination. The bamboos in transverse direction will prevent boulders from rolling down the slope during ballasting. For the West Guide Bund, 141 mattresses were fabricated and placed in a period of 5 months. Some of the mattresses had to be 155 meters long, and these are the largest fascine mattresses ever placed in the world. The construction, placing, and ballasting of the fascine mattresses is mainly done by Bangladeshi after being trained by the contractor. Altogether, some 5,000 Bangladeshi are employed on the project for the river training works in the housing area, on the bridge, and on road construction. Immediately after completion of the trimming of the sand slopes of the West Guide Bund, the fascine mattresses must be placed and ballasted. They are towed to their final position. First, they are anchored with concrete blocks to the upper slope. With the help of the sinking pontoon, Vianen, the fascine mattress is then lowered in place. It is sunk by ballasting it with river boulders. When the fascine mattress has been placed on the underwater slope, the 50 centimeters thick rock layer can be dumped. This rock layer, as well as the rock for the earlier mentioned falling apron, is dumped by a special ship, a so-called side stone dumping vessel. The vessel is fitted out with much advanced equipment, like a dynamic positioning system fed by satellite positioning. The computer calculates exactly where the rock has to be dumped. Rock up to 115 kilos is placed at the falling apron. Rock up to 60 kilos is used for the slope protection. Rock up to 100 kilos is used for the slope to 100 meters on both sides of the bridge's axis. When the Pompeii has dumped the rock, the survey department comes into action again. The survey boat measures the layer of rock placed and checks to see whether it meets the specification. Afterwards, the survey department discusses with the crew of the stone dumping vessel whether and where the layer thickness must be increased. The next trip is made with the new computer data of the survey department on board. Meanwhile, above water, the rest of the slopes are finished. First, the slope is covered with geotextile. With plant and manpower, the rocks weighing up to 60 kilos are put in place. The top slope gets a layer of open stone asphalt. The asphalt plant operates at full capacity to get this job done. Besides the open stone asphalt grouting, mortar is also used. The material is poured across joints between the open stone asphalt and the rocks. In early August 1996, the last rock is dumped and the West Guide bund is complete. In the 1996-1997 dry season, the East Guide bund is constructed in a similar manner. Meanwhile, all piles for the bridge have been driven, and the placing of pile caps and concreting of pier stems is well underway. For the bridge superstructure, 1,257 segments will be made in a huge pre-casting yard. This pre-casting yard produces 18.5 meter wide bridge segments like clockwork. The segments are built in 9 different cells, each producing a full range of segments differing in height. After placing the reinforcement frames, concrete is poured. Curing of the concrete is accelerated by using steam. For that purpose, each cell can be screened off by closing huge curtains. After 14 hours curing at 50 degrees centigrade, the cured segment can be transported to the storage yard. A special vehicle is used to transport the segments from storage yard to the bridge. On the bridge, an erection gantry takes over. Each time it places 2 segments simultaneously, and in this manner builds out a balanced cantilever bridge section from the 177 tons pier head unit placed first on the pier stem. The 2 segments are fixed against the units already placed by using a special glue and pre-stressing techniques. Each time a 100 meters long cantilever section is complete, it will be stitched against the section already in place. Six or 7 spans joined together will form a continuous 600 or 700 meter long bridge section. In between these sections, there is an expansion joint. Slowly, but steadily, the bridge grows across the river. Each month, some 300 meters of bridge is erected, and it is therefore expected that the bridge will be open for traffic in July 1998. The approach roads at both sides of the river are constructed by the Korean contractor Samwan. On the east side, 15 kilometers of road will be constructed, while at the west side this will be 14 kilometers. Also for the road construction, a combination is used of manual labor and sophisticated road building equipment. As is usual in Bangladesh, the road is built on an embankment to prevent flooding during the monsoon season. Numerous culverts and slab bridges in the road approaches must ensure that cross-drainage of the agricultural land is not hampered in any way. In April 1997, the project looked at from the air was in an advanced stage of completion. Mr. Abdul Mujid Chowdhury, Secretary Jamuna Bridge Division and Executive Director of the Jamuna Bridge Authority, was asked to summarize the situation.
Today we had a look at all the components of the project from our helicopter, and it's a magnificent view. It looks so many components. The river training works almost completed, being done by Hemvo. The bridge is being done by Hyundai. It's progressing quite satisfactorily. And the approach roads are being done by Samwan Corporation. That's also progressing fast. And at this stage, the view from the top is very nice. So many activities going on. It's magnificent.
In 1998, the Jamuna Multipurpose Bridge, an old dream of the Bangladeshi, will have become a reality, and communication across the mighty Brahmaputra will be much easier than before. Also, locally, the river will then have been tamed, thanks to Dutch expertise in river engineering, design, dredging, and marine construction.